All right, let's just jump right in. For more than 100 years, our whole understanding of the universe has been split right down the middle. Seriously, we have two sets of rules for reality, and they just do not get along. But what if that conflict isn't some big mistake? What if it's actually a giant cosmic clue pointing to a truth about reality that's way, way deeper than we ever imagined?
So, on one side, you've got Einstein's General Relativity. It's this beautiful, elegant masterpiece that describes the grand dance of planets, stars, and entire galaxies. Then, on the other side, you have quantum mechanics, the totally bizarre, probabilistic, frankly weird rulebook for the universe at the tiniest subatomic scales. Both of these are absolute pillars of modern physics. They work perfectly in their own domains.
And here's the rub. When you need them to work together, say inside a black hole or right at the Big Bang, the whole system just crashes. The math completely breaks down. It predicts these impossible points of infinite density called singularities. It's basically a 100-year-old error message from the universe that we've been trying to figure out ever since.
But what if we've been looking at this whole thing backwards? What if this clash of the titans, this conflict between our two greatest theories, isn't a bug, but a feature? A clue that could lead us, like cosmic detectives, to a hidden layer of reality we never even knew was there. You see, for decades, the main assumption was pretty straightforward. Einstein's gravity must be the one that needs fixing. The whole mission was to quantize it, to somehow force it to fit into the strange world of quantum rules.
And look, this led to some absolutely brilliant ideas. You've probably heard of them. String theory says, hey, what if all particles are just tiny vibrating strings? Then there's loop quantum gravity, which suggests that space-time itself isn't a smooth sheet, but is actually pixelated, made of these indivisible little chunks. Both are just fascinating attempts to crack the code.
But here's the reality check. So far, it hasn't worked. At all. When physicists try to shove gravity into that quantum box, the math just spits out nonsense. These infinities that basically scream, nope, wrong answer, you're missing a huge piece of the puzzle.
So, if it's this hard to force gravity into the quantum framework, maybe we've got the whole relationship turned around. What if gravity isn't the fundamental thing we need to change?
And that leads us to this revolutionary idea, emergent gravity. This theory suggests that gravity isn't fundamental at all. Instead, it just arises from something deeper, kind of like other things we experience every single day without even thinking about it.
To really get this, let's ask a really simple question. What is temperature? I mean, it feels totally real, right? A fire's hot, ice is cold. It seems like a fundamental property of an object. But is it?
Well, here's the wild part. If you could zoom in on a single water molecule, the question, what's its temperature, doesn't even make sense. A single molecule can't be hot or cold. The idea of temperature only shows up when you have trillions of them all jiggling around. It's just the average energy of their collective wiggling.
Temperature is an emergent property. It's not there at the fundamental level of one particle, but it appears from the statistical, messy behavior of a massive group. It's a real-world effect born from microscopic chaos.
So here's the billion-dollar question, right? Could gravity be the exact same kind of thing? Could the force that's holding you in your chair right now be nothing more than a statistical side effect? A kind of thermodynamic force that emerges from countless invisible quantum interactions, just like heat emerges from wiggling molecules?
Now, I know this sounds like something straight out of science fiction, but the amazing part is we're at a moment in history where physicists are actually designing real experiments to find out. We're finally moving from pure theory into the hunt for actual, real-world clues.
One of the most exciting tests out there tries to answer a question that the legendary Richard Feynman first asked. Can gravity create quantum entanglement? You know, that spooky quantum connection where two particles become linked so that measuring one instantly affects the other, no matter how far apart they are. The experiment is designed to see if gravity, and gravity alone, can create that link between them. And the thinking was, if the answer is yes, if gravity can entangle two particles, then that would be incredibly powerful evidence that gravity has to be quantum. It would be the smoking gun. Case closed. Simple, right?
Well, like any good detective story,
There's a plot twist.
a study that came out recently suggests that even a purely classical non-quantum gravity, like Einstein's version, might be able to cause entanglement under very specific conditions. Now, this doesn't kill the experiment, but it sure does mean that interpreting the results just got a whole lot more complicated. That smoking gun might not be so simple after all.
So with that in mind, let's look at a different approach.
A brand new theory from late 2023 proposes a kind of middle ground, something that's not quite classical and not quite quantum. It suggests that space-time is mostly classical, just like Einstein told us, but that the quantum world is constantly kicking it, causing it to randomly fluctuate, to literally wobble on a microscopic scale.
Okay, so how on earth could you test that? The proposed experiment is just ingenious. You take an object with an incredibly precise mass, like the international standard for the kilogram, and you just weigh it, over and over and over again, with almost unimaginable accuracy. If this new theory is right, its measured weight should fluctuate. Just a tiny, tiny bit, because the very fabric of space-time it's sitting on is wobbling beneath it.
Okay, let's take a big step back for a second, because this idea of emergent gravity points to an even more profound, even more mind-bending possibility, that our universe isn't fundamentally made of matter and energy, but of pure information.
This is what's known as the holographic principle. Think about the little hologram on your credit card. It's a flat, two-dimensional surface, right? But it contains all the information needed to project a full three-dimensional image. The holographic principle suggests that our entire 3D universe could be just like that, a projection of quantum information that lives on some distant 2D boundary.
In this picture, space-time and gravity aren't the fundamental canvas that reality is painted on. No, they are the painting itself. The geometry of space, the very idea of distance, might just be a physical map of quantum entanglement. The more entangled two bits of information are, the closer together they appear to be in our projected 3D reality.
So, is gravity fundamental or is it an illusion? The case is obviously far from closed, but what's so incredibly exciting is that for the first time in history, we're moving past just thinking about it. We have actual tangible leads that we can follow up on and test in a lab.
It seems that century-old conflict between our two greatest theories may have been pointing us here the whole time, to a universe where the solid world we see around us is just a shadow, an emergent hologram projected from a hidden reality made of pure quantum information. The hunt for the answer is officially on, and you can bet it's going to reshape everything we think we know.